Okay, so here's another example. I guess this is associated with class 22, although class 23, we kind of build off of it. But anyway, we're going to take the spreadsheet that we made and we're going to solve this problem and do a couple of what if things as well. So here it is. This is a problem from White's 7th edition. It's the example 616, and we have water at at our standard density, and then we're using the kinematic viscosity this time. And between these two reservoirs at 0.2 cubic feet per second through a 400 foot of pipe, 2-inch pipe again. Wish we had picked something else instead of 2-inch pipe. But we're doing 2-inch pipe again, and there's several minor losses, and the roughness. They actually gave us the roughness ratio, so we want to compute the pump horsepower required, and we have the answer somewhere. Where did I do with it? So I have like the solution already from White's book. And so let's see how close we can get to it. So there's going to be some certain differences between our values because this is out of a different book. So let me see. Let's switch over to our spreadsheet over here. All right. So I'm going to copy this. And I've already done this before, so I'm going to stick them right next to this other guy where I have the answer. And I'm like, just do the White example. I'll delete this later. But okay, so I don't need this pump curve, so I'm going to take him out for right now. And I have this in here, so I'll paste him over so we can see what there. All right, so here is what we on here is what we had for the previous example in the previous video. We'll try to get these worked out. All right, so in this scenario with an open reservoir, this is gonna be atmospheric, and this is atmospheric, right? So we got P1 and P2 are 0. This elevation change, you can see that it's going from 20 feet to 120 feet. So this will be 20 feet here, and then Z2 is 120 feet. They told us the total length is 400. The diameter is, we'll go back to 2 inches again. They gave this as an input for the roughness, this relative roughness ratio. We got a couple choices. We could go, get rid of this and then change that right there. Could make that an input. That's probably the easiest way to do, but we're taking away some of the versatility that we'd have. But let's go ahead and do this 0.001, which isn't all that much different. But I'll delete this one, and I might leave myself a note or something that I have that this became an input. That's what the yellow means. Let's see, what else did they do? They gave us the kinematic viscosity instead of the viscosity here. So I'm going to go ahead and cheat here a little bit. So maybe I'll let myself know that I did something different by changing the color right here. And I will take my 0 point, let's see how many zeros does it look like. There's 4 zeros, 0, 0, 0, 0, 1, 1, and multiply that by my density. And that's going to get me, I'm not sure I did that right, tell you the truth. It should get closer. Let me see, what did I do before? No, that was right. Okay. So anyway, I put this in here so that I'll just remember that I changed something, made it slightly different than what's usually done. Then let's see, they also did a thing where they did 0.2 cubic feet per second instead of doing gallons per minute. So I might reverse the way this is right here, let's see, and change that to an input and go 0.2 right here, and then change this to an output instead. Just for my own sake, because I like to compare. So I'm going to take, let's see, what are we going to do? We're going to make this that times 7.48 and times 60, right? So it ends up being 90. Of close to 90 gallons per minute. All right, so now we want to go through these minor losses. All right, and that's where things are also going to change, because this text, the textbook from whence this came, that's a weird way to say it. From whence, I guess so. All right. So we go camera here. Use different values right here. So look, they have a sharp entrance, and they use 0.5 versus us, where I used the 0.8. So we'll change that, and maybe I'll make some kind of mark in here to know that I changed this just for later use. We also have a globe valve. They only have one globe valve, but he is 6.9 versus the 10 that this other book was using right here. So there's one here, and we'll do 6.9. And color him. Let us know that we've made him a change to this. 12-inch bend is 0.25. We don't even have that as an option in ours. So let's put him in as an other, maybe. Hopefully we don't have to use an other. 0.25. Let's make this thing expands out to 0.25. And we have a regular elbow is 0.95. And do they only have one regular elbow? Yeah, I guess that's the regular elbow up there. So that's a threaded one. And then once again, they used something else. They used a 0.95 instead of a 1.5. Let's make that yellow, and let's make sure we can see the digits. And a half-closed gate valve. All right, so maybe our gate valve. Let's put it here for the gate valve. And there's one, and let's go for 2.7. 2.7 for the half-closed gate valve right there, and then have a sharp exit. Sharp exit. I think I might have. I'll get rid of the check valve. Have the exit is 1. We should be having a 12.3. So I have something wrong here somewhere. A threaded branch. There you go. 12.3 is what they have. It's what we have. And let's see, what other things might they have done in comparison, right? So here's what they have by the hand calculations from White's. Of course, we got the rate velocity. You should have got that, 9.17. Should get the same Reynolds number. Let's check the Reynolds number in ours. Yeah, pretty close. Yeah, 139,000 right there. Okay. Their E over D and the F, let's see, they got 2.16. That's probably a pretty good difference right there. 0.02139 is what we got, right? So that's a pretty good difference. You know, it's gonna have an effect. So they're saying that the pump head required is 184 compared to 183.1. And then, of course, so the power should be pretty close, 4.2. And there you go, 4.158. So that's we have this set up to succeed. And I decided to do a what-if analysis here. A what if to extend this problem to be more of a, I don't know, maybe of a design, like, okay, so what kind of flow rate, first off, will we need to be able to get 5 horsepower? Like, what would 5 horsepower accomplish? So we find the question, how find the flow rate for 5 horsepower. So we're going to change this to 5. That's not really all that difficult. It's not going to change it too much. By changing that cell right there, right? And so we're going to put that as an input. So we get there, we say, 98.77 gallons per minute will be what causes 5 horsepower. What if instead we want 150 gallons per minute? Well, first off, I probably need to calculate this backwards. But if I'm really lazy, now that I know goal seek, I can just turn that into 150 by changing that value right there. Like, how lazy am I? Boom. Boom. Okay, so there you go. I could have just calculated that with, a couple of seconds, but I went ahead and did the little goal seek for it. So you can see that it's 12 horsepower. Now to do 150 gallons per minute. What if we don't have that? We only have 5 horsepower. Can we change the diameter to get this to 5 horsepower? So we go to the goal seek, and we're going to want to set that to 5 by changing, going to move you out the diameter. And there you go. So we have, it's just about 3 inches. And you can see here's the long version of the thing. Of course, you can't make a pipe exactly that size, but we might be able, we will find a pipe that's close enough. Maybe if we use our nominal pipe sizes right here, and we look through here, 3 is actually 3.25, and if we use the standard Schedule 40 of we'll take 3.5 and subtract out 0.216 times 2. We get 3.068. So let's try that out. 3.068. And bing, bang, boom. We got pretty close, right? So maybe that's going to be acceptable, and we can pick and specify a 3-inch pipe to achieve that design goal. So this is another example of using the spreadsheet to accomplish a task. We're going to use it for some more things, so look for more videos. And have a good Thanksgiving.